So I'm just going to warn you up front. This topic is going to be a pain. Now, what I have here in the notes is actually meant for 2 class periods. I will not attempt to get through all of this today. How far I'm going to get in these 5 or 6 pages, I don't remember. We'll see what happens. And I'm certainly not going to rush through it. So we're moving on from filter spaces, linear operator, that sort of thing. Deal with how we solve certain ODEs by expressing the solution as a power series with unknown coefficients, and the goal is to find those coefficients. And soon I'll put out the homework assignment for this section. I want to curate it a little bit before I put it out there. So the assignment will be a little more humane than last time I taught this class 9 years ago. Okay, so assuming I get to a decent stopping point, we'll see where we are time-wise as far as the homework questions. Okay, now we have a proper thing showing up on camera, so that's good. Because that's my view of looking at the monitor back in the back of the room, and what I was showing before was just wrong. Inelegant, we'll put it that way. Okay, so today it's all about what is called Frobenius' method for coming up with a power series solution to an ODE. So the kind of ODE that we're going to look at is something of this form. So it's linear, second order, and homogeneous, meaning at the right-hand side is 0. For some coefficients p and q that may depend on x. In some cases, the coefficients p and q might be undefined at a certain point. For example, it's not unreasonable to have say p of x equal to 1 over x. So points like that where the ODE has a singularity will need a special consideration. Now, because it is a second order ODE, you can find 2 linearly independent solutions, so y1 of x, y2 of x. So solutions that are not scalar multiples of each other. What we're going to do today is mainly focusing on at least finding one solution. And then the next section, 7.6, is about how you can use a technique that you would have actually seen in a first differential equations course called reduction of order to obtain the second solution from the first. That'll be easier than going back to the power series approach and carrying it out again. Okay. And if you do have those 2 linearly independent solutions, this is the general solution of the ODE. So all solutions of the second order linear homogeneous ODE have this form. It's a linear combination of 2 solutions, y1 and y2 that you find. Okay. So what kind of solution are we looking for? Something of this form. And I guess it might not be technically correct. Normally the power series is where you have an infinite sum coefficients x minus a center raised to some power. Oh, whoops. That x should not be there. Okay. Normally raised to an integer power, but we have this extra term here in the exponent, j plus s, where s does not necessarily have to be an integer. So what we first have to be to find out what are the possible values of s that we can have. And then we go about finding all the coefficients, a0, a1, a2, and so on. And generally we're going to find them in order, increasing index. X naught, this value, is referred to as the center of the power series. Usually that will be 0. So it's best not to just try to describe a general method, but rather illustrate Frobenius' method using examples. Okay, so the first one will be a linear oscillator, also known as a simple harmonic oscillator, or SHO, but when sometimes the textbook refers to it by the acronym. So this is a relatively simple ODE. It's actually one that you would have learned to solve in your first differential equations class, but this is going to be a in power series form, whereas when you arrive at it in a class like that, it would involve like sines and cosines. Okay, so omega squared here, that is a constant. So the way Frobenius' method works is you assume your solution has this form, and you substitute this form into ODE. Now that's going to require computing certainly its second derivative, possibly its first derivative as well, but you don't need that in this example. That means applying a power rule to each one of these terms. Now what we're going to do here is we're going to assume this power series, and we use a center of 0. And this is what we get. Now, how do we arrive at this? This right here is the second derivative of x to the j plus s. Because you pull the exponent down, that's j plus s. And then you get first derivative would be x to the j plus s minus 1. So you take that exponent, j plus s minus 1, pull back down 2, and you subtract 1 from the exponent again. So this right here is that second derivative. And then you have plus omega squared times just plain old y, so that's where this xj plus s comes from. And then the whole thing is equal to 0. Okay. Add a little elaboration here. It's a good idea to have in mind, and you all know the power rule for computing just a derivative once. But to jump directly to second derivative power rule, so exponent times exponent minus 1 times x to exponent minus 2. It's like cut the chase there. All right. So now we need to write this equation in such a way as to figure out what the coefficients a0, a1, a2, etc. must be for this to be satisfied. Well, any questions up to this point? Okay. Now, actually, before I continue to the next step, you keep in mind here we have x to the j plus f minus 2, and then x to the j plus s. So, we don't know what s is at this point, but j starts from 0 and keeps increasing. So, the lowest powers of x that we can have starts with j plus s minus 2, and then j plus s minus 1, and so forth. The lowest power we can have here is, so the lowest power of x we can have here is x to the s minus 2, and then x to the s minus 1, and so on. Here, the smallest power of x we can have is x to the is x to the s. So this is going to contribute 2 powers of x that we won't have over here. So it's a good idea for that reason to write out the terms involving these lowest 2 powers of x separately from the rest. And that's what I actually do in the next step. So here we have the term of with x to the s minus 2, and then x to the s minus 1, and then all other terms in the entire series are written here. So notice here I have the sum j equals 2 to infinity of all this. That's because the first terms corresponding to j equals 0 and j equals 1 are written over here. And then this I haven't actually disturbed. I've factored out the omega squared, but that's it. Now here we have x to the j plus s minus 2. Here we have x to the j plus s. But we also have j going from 2 to infinity over here, and j going from 0 to infinity over here. It's a good idea to write all of this in such a way that you have x to the j plus s throughout. So what that means is you're going to shift the indices of this summation. So how that works is in this expression here, wherever you see j, you replace it by j plus 2. And you see how that changed everything down here. Because now I have x to the j plus s. And then here I have a j plus 2, and then j plus s plus 2, and then j plus s plus 1 instead of minus 1. But then to compensate for that, you reduce the starting index by 2. So you add 2 within here, subtract 2 out here. That's how you shift the summations index. And that makes everything line up, because now both sums are from j equals 0 to infinity. Both sums have x to the j plus s, so you can combine them into 1, and xj plus f can be factored out of your expression inside the sum. Now I should mention, it's not part of this example, but if there had been a first derivative term, you would have a sum in between here that would be from j equals 1 to infinity, and you have x to the j plus s minus 1. You would do a similar shift for that summation if you had it, but you're only shifting by j by 1 instead of 2. The idea is, after you peel off the terms of the 2 lowest degrees, x to the s minus 2, x to the s minus 1, everything else gets combined into one summation, j equals 0 to infinity, and then you have something times x to the j plus s. It can always be done for this type of ODE. And we're considering now category ODEs, second order, linear, homogeneous. And for those kind of equations, this can always be done. So index shift of 2 for the second derivative, index shift of 1 for the first derivative. This you can leave as is, and now you have this. Because now the ODE with the power series substituted in is written in a form that allows us to solve for the coefficients aj. But before I talk about how we do that, are there any questions about how we got to this point?
Will it always be only two people?
Those are the two terms? Yes.
Only two.
Yes, and the reason for that is because it is a second order ODE. Like if we were doing a third order, we pull out three terms. And because you're starting with x to the j plus s, and then differentiating gives you lower degrees, two lower degrees, that's what we kill off.
So to confirm, if you had three of these terms, would you have like three lowest degree terms?
Yeah, if this had been a third order ODE, then you would have like x to the j plus s minus 3 in there somewhere from taking the third derivative of that series. You would need three terms out here, and you would be doing index shifts of shifting by 1, 2, and 3. That's how it would generalize, and we're not going to touch that. Oh yeah, but it helps to see like what's the pattern. Yeah. Where you do a concrete example or not. Other questions? Okay, this equation has to be satisfied for all x. So what that means is all coefficients of any power of x in this whole expression must be 0. Like, so this expression here, a0 times sf minus 1 must be 0. This has to be 0. Whatever is multiplying the power of x, this whole expression in the square brackets must be 0 for each value of j from 0 on up. So that gives you a system of equations, infinitely many equations, to solve for, like first we'll deal with a0, then with a1. And notice here we have aj plus 2 and aj. And we'll see how we can use that in a bit to get all the coefficients. But we start with the lowest power of x. And we're going to require that a0 be non-zero, because we don't know what s is. It may or may not be an integer. Because we have some flexibility about what s must be. We got to start somewhere. So we're just going to require the first term of this power series be non-zero, and then that will dictate what the value of s must be. So, because this whole expression multiplying x to the s minus 2 must be 0, but a0 is forbidden to be 0, the rest of this, s times s minus 1, that must be 0. And this leads to what's called the indicial equation. And that gives us two possibilities for s. Either s must be 0 or s must be 1. And it makes sense that there would be two possibilities because there are two linearly independent solutions. So for each choice of s you make, that's going to lead to a different solution. And let's briefly examine these two possibilities. When we go to the second term, suppose that s equals 0. If we choose that, then this is going to be 0. So this second term will be 0 no matter what. A1 can be chosen to be anything. And we're still covered. But if s equals 1, then we get a1 times 2 times x to the s minus 1. That means in that case, a1 has to be 0. So since we have one possibility where a1 can be chosen however we like, and the other possibility that A1 must be 0. We're just going to let A1 be 0, just to make things easier. Now, the rest of the coefficients come from setting this equal to 0. So all I do is I take this in square brackets, set it equal to 0, and I solve for the new coefficient, and one of a higher index. I'm going to solve for aj plus 2 in terms of aj. And that gives me this. So each coefficient depends on the one 2 before it. So we have to choose A0 equal to 0. Now, this is a homogeneous ODE. So any scalar multiple of a solution is also a solution. So we can choose A0 to be anything to be. We can just let A0 equal to 1. So then A2 would be determined from A0. A4 would be determined by A2, and so on. On the other hand, we're saying that A1 is 0. Well, because A1 is 0, then A3 must be 0. Then A5 comes from A3. So all the odd numbered coefficients are going to turn out to be 0 in this case. We're only going to have even numbered terms. Any questions up to this point? All right, so we're going to let x equal 0 and see what happens. The idea is to compute some coefficients using this recurrence relation and see what patterns, if any, we get. Now, so A2, I go ahead and compute from A0. I haven't stipulated the value of A0 yet, but a little later. And then here's A4 in terms of A2, just from a recurrence relation. But A2 is in terms of A0. So that means I can express A4 in terms of A0 also, and this is what I get. But similarly, A6 comes from A4, but then I substitute the expression for A4 in terms of A0. So everything is a multiple of A0. So if we look at what we have here so far for A2, A4, A6, what patterns do we see? There are a few of them. And just look at the final formulas that are in terms of A0.
Denominator is a multiple
Denominator what?
are a multiple of the j.
They are. Yeah, they do include as a factor.
And well, no, never mind.
Okay, what else do we have? Anybody? So, okay, so it's observed that the denominators have j itself as a factor. What other factors do they have?
I mean, 24 times 30 is 720.
It is. Okay, so, all right. So for 4, you got 24. And you multiply by 30, which factors into what? Yes. Now let's go a step back. 2 goes to 24. You're multiplying by 12. 12 factors into what?
24.
I mean, 12 factors into
6 and 2.
4 and 3. Yeah. So to get from here to here, we multiply by 3 and 4. From here to here, we multiply by 5 and 6. What are these numbers? 7, 20, 24. Well, yes, they're factorial. 2 factorial, 4 factorial, 6 factorial. It's j factorial. What about the omegas? What's happening with them? What pattern do we have there? Yeah. So it matches the index. So we have omega to the j over j factorial, but only for even j. Here's one other thing that's happening with these coefficients besides that. Yeah, the signs are alternating. So this is what we have in general. So because it's only even number, we have a sub 2p minus 1 to the p to make it flip each time p increases. A0 if it's sitting here doing nothing. Omega to the same even power, and then factorial. So now what we can do is here's our power series. A0 we just factor out. Here's our formula to the p we have j, a2j, x to the 2j. And remember, before we had x to the j plus s, but we're only considering even j, so that's why it's 2j. And s has been chosen to be 0 in this case. But this is the Maclaurin series for cosine. Cosine omega x, which I mentioned before, like when you would solve this kind of ODE in regular ODE class, you would get sine or cosine. So here we see we get when we choose s equals 0, we get cosine. Any questions about how we arrived at that? We choose s equal 1. We see a similar thing happening. We still have the even powers of omega that match the index. So A0 sitting there, we still have the alternating signs, but the numbers down below are different. What are we getting now? Like, what do you multiply by to get from 6 to 20, and how that breaks down? It is a factorial. 120 is, what factorial is that?
5 factorial.
What?
5.
Yes, 5 factorial. And 5040 is 7 factorial. Because, well, look this way. From 6 to 120, you multiply by 20, 4 times 5. Okay, from here to here, multiply by 6 times 7. Like, wouldn't expect you to know that. So, all right. So this is formula now. Same formula as before, except we have 2p plus 1 factorial down below. And then we substitute that into the power series, but now we have x to the 2j plus 1. Why? Because your general power series is x to the j plus s, and s is now 1. So that's why we have this plus 1 here. Now, here we have omega to the 2j. Here we have x to the 2j plus 1. But I'd like to package the omega and the x together. So what I'm going to do is multiply and divide by omega. So we have omega in the denominator outside, omega in the numerator inside. So now we have omega to the 2j plus 1, x to the 2j plus 1. So now I have omega x, the whole thing, to the 2j plus 1. And this is the Maclaurin series for sine of omega x. So sure enough, we get cosine or sine, depending on, so there are two options for s led to the two linearly dependent solutions, cosine omega x, sine omega x. But what you can also do is, and this is something I'll get into in the next section, you pick one value of s, work it out, and then forget about power series and use reduction order to get the second solution. It turned out to be easier. So this is Frobenius' method, that you assume y of x is a power series where you have an extra term s in the exponent that's not necessarily an integer. So it's not the kind of power series that you're accustomed to like from Cal 3. Substitute that into the ODE. Peel off the two terms of the two lowest degrees, which would be x to the s minus 2, x to the s minus 1. Use those to get your initial equation for the A0 term that gives you possibilities for s. And then basically just making sure that all the terms in your power series equation have coefficients that are 0. And that is how you solve for the coefficients AJ in your power series. Up to it. Okay. Once you have this, definitely substitute it into the direct equation to make sure it really is satisfied. There are many, many opportunities to make a mistake. Process like this. That's why I did not do very many homework problems. Okay. Also keep in mind, because it's a power series do not necessarily converge. It'd be a good idea to apply some sort of convergence test. For example, the ratio test is often useful for power series to determine for which x do they converge. So these Maclaurin series for sine and cosine, they are known to converge for all x, the entire real number line. But there are some that have their have a radius, a finite radius of convergence. They only converge for x within a certain interval centered at x naught. That's something to be mindful of. But if it doesn't converge, then it's not exactly a viable solution. Now, in a situation like we just had this example, where your solution has only odd powers of x, or only even powers, then you have some symmetry. If you have all odd powers of x, then the solution is an odd function, meaning that if you negate x, then that has the effect of negating f of x. So sine is an example of an odd function. X cubed, x to the fifth, all odd functions. If you have only even powers of x, then you have an even function where negating x does not change the function value. So cosine, x squared, x to the fourth, etc. Those are all even functions. Now, it turns out that you don't have to go through the whole Frobenius method to find out if your solutions are going to have this kind of symmetry. Because these ODEs have this form. We have a differential operator applied to y of x is equal to 0. And this operator L of x is going to have differentiation operators, is going to have coefficients that are functions of x. So what you can do is, in your differential operator, you can replace, that second minus shouldn't be there. Okay, so if negating x does not change the ODE at all, then the operator is even. Whereas if you if negating x okay. Oh, okay. Actually, I'm going to focus only on the even case. So what that tells you is that whatever solution y of x you get, y of minus x is also a solution. So just by examining the ODE before you even do anything towards finding a solution, you can detect if there's going to be symmetry. Now, so let's suppose you find a solution y of x. And then you go ahead and replace x with minus x and see what you get. Now, one thing that can happen is they might be linearly dependent. They might be scalar multiples of each other. And in that case, if one's a scalar multiple of the other, and the constant of proportionality is positive, it's an even function. If it's negative, then it's an odd function. If y of x and y minus x are not multiples of each other, then you don't have them being even or odd. Instead, you can take these linear combinations. So if y itself is neither even nor odd, this combination, y of x plus y of minus x, that is guaranteed to be an even function. This is guaranteed to be an odd function. So, so if this property is satisfied, then that tells you that you can always get two linearly independent solutions that are even or odd. Oh wait. Sorry, not necessarily linearly independent, like in this case, but in this case it would be. But yeah. So even operator allows you to get even or odd solutions. And that can be helpful to know if you're going to use Frobenius to find a solution. Because let's suppose you examine your ODE, you set x equal to minus x, you get the same ODE, you see it's even over symmetry. But then you go ahead and use Frobenius' method, and then it's reasonable to expect, at least, that you're going to get something that has like only even powers or only odd powers. In which case, that would be like an even function or an odd function. So at least give advance warning that it's coming. Okay. On the one hand, there's a good amount of time left. On the other hand, I've made a lot of headway through the notes. Thanks. Yes, I'm more than halfway through the notes. Well, if I were to continue, then I don't think I might fall short of finishing that. Okay. But the thing is, I budgeted today's class and next Tuesday's for this section, and so I think this would be a good time to pause and see if there are any homework questions that have been lingering. Yes.
5.3, number 3.
Okay. So I need to unshare and reshare. Okay, 5, 3, 3,
Yeah,
okay.
just part of it.
Okay, so, so the idea is, okay, so you have these three functions, x1, x2, x3, corresponding to your, three independent variables. So what happens is when you actually work out this operator, for instance, applied to x1, then the result that you get is going to be a linear combination of x1, x2, and x3. And that will tell you how to fill the first column of your matrix. Okay, actually, I'm going to write this into the notes. Okay, so here's my stopping point for today. Okay. All right. So, so the IJ entry, right, so seeing the IJ entry of the operator AK, or A1 or A2, so what you do is you compute the operator AK applied to function, the basis function phi j. And then what you do is you, and I'm going to call that result psi j. All right. And then you write the following. Psi j is equal to a linear combination okay. Of column J in the matrix for the operator AK. And then so, okay, and then you move to the next basis function, phi 2, which is x2. Work out what the result is. That's a linear combination of phi 1, phi 2, phi 3 that fills the second column, and then you fill the whole matrix from there. Does that make sense?
So what would five, like, one, would this be equal to 0 or 1, depending on the,
Yes, yeah. So we use the fact that the partial derivative of xi with respect to xj is equal to the Kronecker delta, which is 1 if ij are equal 0 otherwise. Because they're independent variables. What I'm doing here is being sloppy with my notation. I'm here referring to the operator, here referring to the matrix. I'm basically identifying the operator with the matrix. I should give this a different symbol, but I'm being lazy. Other questions about this one or another one? So what happens later in the problem, here we have a given vector psi that's a linear combination of your basis functions of these coefficients, 1, -2, and 3. So what should happen is that if you were to form your matrix for, say, A1, and then multiply it by the vector 1, -2, 3, then that gives you coefficients of phi 1, phi 2, phi 3 for the result. And that should be equal to what you would get if you just apply the operator A1 to this function directly and saw that wrote it in terms of a linear combination of phi 1, phi 2, phi 3. And so you can either, so applying the operator and getting the coefficients would be equivalent to taking the coefficients, performing the matrix vector product, and doing the same coefficients as a result. So it relates applying an operator to, so instead of applying the operator to Hilbert space, you're applying it to ordinary vector space, in this case, vectors in R3. And number 4, similarly, the matrix of an operator.
We go through like one of the computations to get like an idea, like do like 1, 1 or something.
Okay. From this?
Yeah. So I'm kind of
Okay. So A1 phi 2. Okay. So that would be a sum. Okay, so just reproducing the operator here. Xi okay, so we have that. But phi 2 is x2. The partial of x2 with respect to xi. But this is going to be, this derivative is going to be 0 unless I is equal to 2, in which case the partial derivative would be 1. So we end up with x2, partial of x2 with respect to x2, which is 1. So we just get x2 as a result. So what that means is the second column of the matrix of A1 is 0, 1, 0, because first element of a column is a coefficient in the result of x1, but there is no x1. There's no x3 either, so this coefficient is 0, and then we just have a plain little x2, so this coefficient is 1. Okay. Not a very interesting example out of it. I think one of A2 would be more interesting, because for that one, yeah, there's more of a chance of getting non-zero terms. I think most entries of the matrix of A1 will be 0. All right, I guess we're calling it good. So let me cover on Tuesday. And I think it'll be time for homework questions then too.